Okay, back to the Northern Hemisphere here. Sean Wright is going to talk about exploration zone in Cerberus containing young and old terrains. Sean, go ahead.
Thank you. Yeah, the title says it all, including Fossae faults and perhaps sugartite distal ejecta.
Take it outside, we'll stop. It'll be good.
I took this from a field geology perspective, particularly when the announcement for this conference came out. I thought, oh, this is the sample return. So you'll see my talk today is mainly based on sample return. I didn't know there was going to be 5 or more visits, but rather astronauts would land, pick up as many diverse suite of rocks as possible, and then leave. So so that the right hand talks to the left hand, MEPAG already commissioned a report on what sample analysis should be, so what samples should be brought back from Mars. They suggest Noachian, igneous or sedimentary, or megabreccia, I forgot to add, both pristine and altered igneous rocks. Admittedly, the pristine igneous rocks might be hard. Impactites and ejecta that I'll talk about a little today. Aeolian sediments and soils and dust are pretty much everywhere. But the last two kind of jumped out at me as it's hard to determine these from, can be hard to determine these with remote sensing, but where are they in relation to the first two? That we always think about impact hydrothermalism, but what about just lava thermally altering or hydrothermally altering old rocks to produce hydrothermally or just thermally metamorphosed rocks? So I chose Cerberus, a little bit dusty that I'll show later, but it's part of the exploration zone. The landing zone is above the threshold. I just kind of do a overall. Elysium's over here. The very tip of the Medusae Fossae formation is over here, and just north of Gusev and Gale Crater. Here for the science regions of interest, I guess if I was a sedimentary geologist, I'd be a lumper and not a splitter. I kind of put all the Noachian terrains into one huge science region of interest. I left out some of the young flood basalts. They're pretty much all of the flat terrain, but mainly wanted to talk about this bullseye or mini easy I'm going to talk about. I chose the field station to be on the border of Noachian and Hesperian / Amazonian. We're not sure, but we could find out by going there. Here you can see the threes right there, a bunch of threes. That's the Fossae. Some of my other, this is a geologic time order too, from oldest to youngest. Some of my ROIs are not listed on this because they're smaller than the resolution of this image, for example. So I'll get into why that's important. But again, this was my exploration zone, but if we like all of the science region of interest, we could easily move the exploration zone to be somewhere else, less dusty or more southern. Just to start with my science regions of interest, really as a terrestrial analog geologist, I try to do comparative planetology, but there is no real analog for these old, maybe 3 or 4 billion Noachian terrains. Kind of look knobby like chert, for example. Remember, a chemical sedimentary rock. It's been dated. This is a very controversial geologic mapping of Cerberus to be early or late Noachian. But I maintain that if a rock's been around for a long time, such as the apex chert of Australia, for example, it's going to have atmospheric and whatever's done around it is going to be overprinted onto the rocks. So perhaps 3-4 billion years of climate change, and then the Hesperian and or Amazonian, maybe throughout volcanics, embay them. So perhaps I'll talk about later, perhaps there's thermal alteration or hydrothermal alteration at that contact. And then anytime there's volcanic rocks, even flood basalts, there's probably going to be ashes and tephras deposited well. But I'll show more ROI 1 throughout the talk today. Don't have much to say about ROI 2 except that these Cerberus flood basalts are extensive. It would be great to get I'm kind of thinking in terms of bridging the gap between field data and sample data of sugartites, for example, to bring those back and figure and kind of compare them to the global crater counts. Here, just for the structural geologists, I thought, why not go study the Fossae? For example, if you look on NSF Fastlane, the most funded NSF Tectonics grants are to field studies of the San Andreas Fault. The most funded NSF geophysics grants are to set up geophysical equipment around not just the San Andreas Fault, but all plate boundaries. So why can't we take those, do those same field studies that are done for San Andreas Fault and other plate boundaries with geophysics instruments and set them up near the Fossae and have structural geologists determine exactly how the Fossae were created. And there's global implications here for Amazonian volcanism, for example. Well mapped here. They suggest some water by Allison Mulder. I'll come back to that later. Oh, I don't really have a slide for region of interest 4. It's just old impact craters, for example. That must be important. It must be a science region of interest. Both Mars rovers just went crater hopping for 10, 11 years, for example. I'm going to talk later about impactites, such as the first Shergotite, Shergatti. That's where atmospheric gases are preserved. If you recall, atmospheric gases inside, trapped inside of impact melt veins inside of Shergatti exactly match the Martian atmosphere. So that was again, science region of interest 4 is just these old impact basins that are all around the old impact craters, excuse me, that are around the website, or around the exploration zone. For science region of interest of 5, I'm going to get a little preview here. You see these really tiny black dots on this CTX image here, and they are pervasive all throughout the exploration zone. Here's an example here of a Themis VNIR image. I chose a Themis VNIR because we know it's 32 kilometers across. So you see every 5 or 6 kilometers you come across these very fresh impact craters. Again, these are all over the exploration zone. And basically, it's a distal ejecta from a fresh raid crater on Mars, Zunil, being 400 or 500 kilometers away from the exploration zone. I'd encourage you to take a look at your own exploration zone. There's 4 or 5 good raid craters on Mars. Sometimes the rays go up to 3,200 kilometers. You have just an extra science region of interest if some hopefully, perhaps Shergotite-like ejecta or whatever Cerberus or the host rock of the raid crater is thrown around Mars. This is something we don't see in terrestrial geology, but rather just the most recent distal ejecta that has landed in that local geology. Here's just showing the, ignore the numbers. I stole this from Publish et al. Oh, by the way, look at all these papers here to determine, look at those other raid craters and see if a distal ejecta ray crosses your own easy exploration zone. This one just shows the dark ejecta craters as well. The exploration zone looks like it has devoid, but I maintain that there's actually just low Mach and high-rise coverage in that area, but it's probably continuous there too. I try to say aqueous floods here because there's flood basalts in Cerberus, but it's under some contention, but some have mapped that 2 to 10 million years ago, the Fossae cracked open or fissured open, and we have rootless cones, also called pseudocraters, indicative of lava flows over ice. Water flow has been mapped by, I forgot to put it on there, Sakamoto et al. And then we see these channels throughout Cerberus as well. My science region of interest 7, instead of our recurrent slope linii, I like to call them hydrated salts now. I like to, since we just determined that. I forgot to cite this too, but I stole this from Alfred McEwen, Mars 2020 talk. And basically, right up in Cerberus, there's one in the southern part of the exploration zone and one just to the north. A third one is a little bit more distant. But it might be possible to check out those RSLs, for example. Cerberus was originally named for this dark feature here. And kind of zooming in on where potentially RSLs might be is just this contact between old Noachian terrain and, as you can see, very flat-lying lava flows of Cerberus. This kind of looks like pasted-on terrain here when I just blew up a CTX image here. But again, these are lava flows that are embaying much older Noachian terrains, and I suggest if we were going to look for metamorphism or hydrothermal metamorphism on Mars, it would be where hot lavas are in contact with rocks. It wasn't possible for Mur-A Spirit, for example, to check out that similar contact in Columbia Hills because it's a rover, but humans could just get a shovel and and perhaps throw it into some machine for the resource ROI and kind of dig out and really examine this contact in detail. I was a conservative here, not too many partially supported. I guess as a scientist I either say yes or I say I don't know. I didn't do a lot of partial support or debated. I guess we can debate, but I didn't debate. I guess if in previous work, I'm just standing on the shoulders of giants here. Other people have had written papers, journal manuscript papers on Cerberus. Sorry I'm not detailed on the resource ROIs. I'm mainly focused on, again, like I said, sample return. Where would I bring back? What samples would I bring back from where on Mars? And again, I was trying to look for something for the volcanologists, for the sedimentologists, for the structural geologists, for example, at the Fossae, and for the Shergotite, because field geology sometimes is incomplete until you can get back to the lab and really say exactly what you had in your hand, exactly what you picked up, and then correlate it with the mapping. Previous authors have suggested that when the Fossae opened up 2 to 10 million years ago, contemporaneous, is when the flooding, aqueous flooding, I want to point out, in Cerberus formed. I'm sorry, again, I'm not specific here. It seems like everyone's kind of said this, that there's going to be dust, there's going to be cobbles of basalt, and whatever those Noachian, perhaps sedimentary rocks are. Again, they're knobby and ridged. I think I forgot to say ridged. I looked for layering, and there's some weak evidence of layering, but knobby and ridge usually indicates sedimentary rocks. Again, they look kind of cherty to me. And again, cherty would be maybe a concentration of more silica than the 45% found in basalt. Resource ROIs, again, I just put a lot of question marks for, mainly just filled out these two columns on the two resource regions of interest. And then if it applied, I filled out, again, mainly the Noachian terrains versus the younger lava flows. I made a rookie mistake. Here's the coverage here. First time using JMARS here. Again, I said I mainly study terrestrial analogs. Some of you are going to smile, but I thought, oh, there's full CRISM coverage, but that was the multispectral data and not the hyperspectral data. So my bad. I'll update this later with the where's hyperspectral coverage of CRISM. This is just high rise. And again, I would suggest more of these, of the contact between ROI1 and ROI2 here. It's seen here. Let's zoom in a little bit, sorry. More of the contact there. One or two swaths can probably pick up that right there, and then maybe a few here. Again, looking for potential RSLs and just the contact between the embayment relationship there. And then, again, this is just another view of it in 3 dimensions. Try to look at this contact in Cerberus. So just to conclude, again, just the title of the paper, Old and Young Terrains with Fossae Faults and perhaps Shergotite Distal Ejecta are the main science ROIs, but also other authors have suggested aqueous flooding. And I didn't really talk about these, but there's nearby formations. They're not exactly in the EZ, but usually planetary geology has shown units find ways to move over the course of 2-3 billion years. But the Medusae Fossae Formation and even Southern Highlands, ancient crater terrains, is nearby the EZ. And then I need to work on this right here. I've learned a lot the past 2 days just to reach that one. And I really appreciate this template. Our astronaut is always looking forward to the Martian sunset, but on the last slide here, he looked to the left there. It's Mark Watney. So anyway, but thank you for your time.
Thank you. We'll go to our second talk.
Actually, Andre just wants to say a couple of words about the movie
Yes.
tonight.
Hey everybody, if you're joining us for the Martian screening tonight, it's at Star Cinema Grill. I'm about to send an email blast to anybody who signed up. The movie is at 6:30 p.m. We should meet there maybe 15-20 minutes before. So in the essence of time, let's try to keep this so we can make it there on time. There will be potatoes in the form of fries. And we're looking forward to seeing you. I'll send you the address and all the information. It's $9 per person, $10 buying online. Let me know if you need any help with that, and I'll help you out. Thank you. Yes.
Can anybody hear me? Is that on? No.
Okay.
Okay.
So our second talk at the session will be Southern Nectaris Fossae, and Ben Boatwright will lead us through the discussion.
That's it.
Yeah, that's good.
All right.
No problem.
Okay. All right. Well, thank you. Again, I'm Ben Boatwright. I'm currently a graduate student at the Department of Earth and Planetary Sciences at Harvard. But actually, most of what I'm going to be telling you about today comes from some of the work I did as an undergrad, doing some Martian hydrology work, particularly looking at valley network formation. And so you'll see one of my ROIs is actually a valley network. So the exploration zone, which I did not point out on the map over here, it's right there. But again, you can see it here, indicated by the white star. This is at the southern end of Nectaris Fossae, which is a large tectonic feature situated about 800 miles south of Valles Marineris. 800 kilometers. So like a few of the other people have said, really, this entire region could be called one giant ROI. You're going to find interesting stuff just about everywhere you look. But my rationale essentially was to choose, as you can see, 4 here, different types of geologic and scientific sites of interest that you might find, and sort of the best examples of each one of those. So the first I'm going to be talking about is a fluvial feature. Again, this is Mawrth Vallis, which is a Noachian valley network system. The second is something I'm calling ice and impacts. So as it turns out, a lot of these impact craters are ice-filled or have some sort of ice feature in them. The third is this sort of volcanic cone up here. And the fourth is Nectaris Fossae itself, whose most southern extents come down here in the form of these sort of subparallel normal faulting features. In terms of resources, unfortunately the spectral characterization of this entire area is rather poor. There's only a single chrism measurement actually was made up here in Nectaris Fossae, which I'll tell you about in a little while. But based on this sort of preponderance of geologic evidence, obviously you've got this big valley network coming that's flowing down downslope this way. I'm sort of positing that there is a strong likelihood that you might find hydrated minerals in this area. All right, so just briefly looking at the habitation zone and landing site. Again, this is right in the middle of this floodplain, so you're going to have very smooth, obstacle-free terrain. And again, just zooming in a little further, here's one potential landing site with a radius of 100 meters. You can see here at this scale, there's some sparse sort of about 100-meter scale dunes, but again, not any particular worry. And again, since this is on this floodplain where there's a strong possibility for hydrated minerals, the resource utilization can be done right on site and really anywhere either within or beyond the habitation zone. And the altitude is 1.9 kilometers, just barely within the prescribed limits. So the first science ROI I wanted to talk about is this fluvial feature. So this is Mawrth Vallis, and as you can see, it's pretty obvious up here. You've got these sort of dendritic patterns, and it's a little harder to see out this direction. They're pretty degraded, but you've got several sort of topographic depressions here that are indicative that at one point these valleys were flowing all the way out into this region, and this red dot is actually the landing site. So at one point you actually get one of these channels that's only about 15 kilometers away. And so generally it's thought that these valley networks formed by the action of flowing liquid water over the surface, much like on Earth. And so, of course, with liquid water, there's the potential for past habitability in this region. And as we look a little closer here, this is in this pink rectangle up here on the left-hand side. Here's sort of the morphology you're going to be seeing if human explorers were to potentially go out to this area. So this is actually about a 200-meter section of some Noachian stratigraphy that you could find. And so, as it turns out, as my research in the past showed, the formation of valley networks was very sensitive to the past climate states that were involved during this time, the late Noachian to early Hesperian, mostly just how much water there was. So if you were to take samples in this area, go up these cliffs, you might find all sorts of things that could tell you about the climate states that were extant at the time in terms of carbon and oxygen isotopes, alteration minerals, all that kind of stuff. So lots of applicable things here. All right, so the second ROI I'm going to talk about is these ice-filled craters. And so as you can see here, some very nice what is called concentric crater fill. And essentially what's going on here is that you have some leftover Amazonian glacial ice that can be potentially several hundreds of meters thick, covered by a relatively thin, maybe 10 to 20 meter layer of this sort of protective dust that is a result of creep sort of down from the crater walls. And so obviously this is a pretty geologically interesting feature, but there are also a lot of implications for biology. Obviously, if you've got this sort of subsurface ice layer protected by this, this overlying dust, I would stretch and say that this could be potential for present habitability if there were to be some sort of melt, perhaps right at the interface between these two layers. And biology or not, if you were to look at this type of feature where there's this a layer of dust interacting with a layer of water, there could be all sorts of interesting chemical cycling. And if there were biology, you could also see maybe some biosignatures, nutrient cycling through this area. And here is the sort of larger crater in the EZ. As you can see, there's some really nice exposed stratigraphy here on the walls. All sorts of just a myriad of sedimentary and aeolian features to look at. And of course, this you don't quite see it here, but you can tell around the rims there's still some really pretty fresh ejecta and some other impact features that you can look at here. This is actually a double crater, as I called it in my abstract. So there's the potential to see all sorts of interesting kind of overlapping impact features here. And the second ice feature actually is these ice mantles. Again, another remnant of some of these recent Amazonian ice ages. And in this case, you're actually getting some ice-rich dust that's settling out of the atmosphere and forming these sort of aprons, or they call them mantles. And since that time, the atmosphere would have dried out. And I'll show you just each of these locations. As you can see, they're all sort of on these sort of these north-facing, or poleward-facing, I should say, rims of the craters, even on some slopes here. And essentially what you're seeing is just some now ice poor debris, aprons and mantles that are desiccated, but still, again, the potential to get some of this sort of atmosphere surface-subsurface cycling and potential for ice. All right, the third one is what I'm saying here is a volcano, or the remnant of a volcano at least. So this red X indicates a topographic high of about 4.3 kilometers. And the prominence, you can't tell from this image very well, is actually about 2 kilometers from sort of the base level. So this is actually quite high. As you can see here, you're also getting some of these main ice mantle outcrops that sort of sweeten the deal a little bit. But this is actually part of the Dalmatia volcanic province, which is actually a sort of rare earlier period of volcanism that happened before Olympus Mons, Tharsis, for example. And I did just want to make a few points about igneous rocks generally, whether you would find it here or wherever else. So with igneous rocks, one of the important things you have to remember, particularly pristine basalt samples like you might find here, is that the sample analysis of these types of igneous rocks could really just open up a whole new avenue, if you will, of discovery in terms of just the very basic questions that we still have unanswered about the geologic history of Mars, particularly the large-scale thermal evolution, the magmatic evolution, tectonic evolution, just all across the board if you were to return an igneous sample. So just something to keep in mind. Finally, I wanted to talk about the Nectaris Fossae. These are, of course, a structural feature that continues on for several hundred kilometers to the north, as I said. But one other interesting little tidbit I wanted to offer would be that one thing that really hasn't been characterized on Mars so far with the exploration we've done with rovers is the idea of looking at just small-scale structural features such as faults and folds. You know, if you were to go out to a road cut on a highway here on Earth, that kind of thing really has not been seen to any great extent. So if you were to go to some of these areas that are sort of cut out of the rock, if you will, you might be able to find that and characterize those things for the first time. And zooming in, again, on this little pink area, as you can see, there's actually some pretty well exposed Noachian stratigraphy here, and this is where that one chrism measurement was made, and it actually found some signs of fluvial activity. So as it turns out, the feature that is traditionally called tectonic may actually also be fluvial, with all of the same benefits that I mentioned before. So just to summarize the ROIs, the science ROIs, all of them meet more than one threshold criteria and a number of qualifying criteria. I'll just leave that up there for people to read at a later time. And so in terms of resources, again, there is no, I should say not yet, spectral evidence of hydrated minerals in this particular area. That's not to say that they cannot be there, obviously. If they were, then there'd be a really huge range of area where you could potentially find these deposits of hydrated minerals at or near the surface, and again, with the same advantages in terms of accessibility and ultimate utilization. And just briefly, resources and some of the other ROIs. Again, ice, that's a really big reservoir of ice right there. And so the problem, though, is it's quite far from the landing site. But you know, if you were somehow to figure out how to overcome the obstacle of distance, this would be a major resource for ice and water, ultimately, as would these ice mantles potentially. But again, they're rather far, but just an idea. And of course, if you were to find volcanic deposits anywhere, those would be good places to get metals. So again, the science criteria, I'm not an atmospheric scientist, so I couldn't really objectively say whether these would be true or not. There's certainly no reason why they couldn't be. And again, for the engineering criteria, I sort of grayed out some of these areas that weren't really applicable just for clarity's sake. Again, all the science ROIs could pretty much also double as resource ROIs if you were to go that route. And the landing site, by and large, satisfies the basic engineering criteria. So in terms of easy data needs, I'm just going to go the same route that most people have and say we need better high-resolution imagery from high-rise of these key science features. And also, especially for this particular area, we really, really need some better spectral measurements just to figure out what this material is made of at the site. Some other things, it would always be nice to have a rover, obviously, and just continuing to characterize this area with some future orbital assets. So just to conclude, I think my main point here really is to sort of to emphasize that, I mean, not only is this kind of region unique geologically speaking, but in terms of the overall mission architecture that we've been talking about, where there's this EZ that's visited multiple times by crews on repeated occasions, this really is the optimal setup, where if you were to land here, you could really just go hop from one to the other over multiple missions and really come back with a brand new science return each time. So, thank you.
So next up, James Skinner. And you'll be talking through here. Okay. Oyama Vallis.
You're right down here. Okay, everybody hear me here? I might have tipped my hand a little bit. I stacked up some maps out there. I don't know if everybody saw them, but if you see them out there, please take one. I think that this emphasizes something that I want to get across is that, you know, we're in the business, we being the USGS and me specifically, in the business of context. This is out of scale with, I've noticed a couple people have cited this map, which is great. I'm trying to get rid of these maps, not for Ken's benefit. Ken's retired. I'm sure he likes a citation, but in the end, he probably doesn't really care. What we're doing, this is your product. This is your product, right? NASA's product is for you guys. It's done on behalf of you guys. by us. So please use these maps. They're out of scale for kind of specifically what we're talking about. There's lots of other maps. Please contact us about these products, okay? So get that out of the way. So I'm going to take a little bit of a different approach here and talk about going and tip my hand again and say, in the end, this is a resource limited place. And what we're going to get out of this is say that, okay, resource limited, but maybe it's so science heavy that it's going to drive some thoughts about what we need to do to, examine other ways to get more information, or can we target different things, or are we just not seeing it the right way? So we're going to look at a pretty benign, fairly boring, but very regular kind of place that occurs in the intercrater plains of the highlands of Mars. This is Hadriacus Palus, and it sits kind of off to the east from Turby Crater. So just a little bit about the rationale. On Earth, basin strata, it's really complicated, and the details of the pre, the sin, and the post-tectonic formation of any one region, especially extensional areas. Extensional areas then are crustal thinning, you have volcanism, and so you have a nice big thick sequence of material that is being shed into a basin. So for example, the Tetons. Right in front of the Tetons is a nice big flat plain. It's beautiful. I mean, we see right here. If you guys have been here, it's really, really nice. But there's a huge sequence of sediment that is sitting right at the bottom of that normal fault, okay? If you could drill down in there, you get a lot of information about how that formed, the events that are moving that crustal block up and being shut off. So there's a lot of information there. Unfortunately, it's covered by this nice green grass and horses. Now, if you were to erode that, here we have the Newark Basin. I wouldn't really point out New Jersey. That's no fault for anybody from New Jersey. But this is the Newark Basin. My wife's from New Jersey, so I think I can say this. But the Newark Basin is an exhumed basin in New Jersey. And so the point here is that here's the same kind of thing where we have a normal fault and you have material being shed into a basin, but it's exhumed. You can see what is going on here, okay? So here the red is kind of fanglomerates or breccias that are being shed off the massif that's being upthrown, finding sequences off in one direction. You also have the volcanics, which are shown in black here. Okay. Let's see. Yeah, so on Mars, one point I want to make here is that on Earth, this is kind of accommodation space, and we think of geologically it is instantaneous. On Mars, it is really instantaneous. I mean, we have a giant impact basin. Now we're talking about basins and these kind of annular spaces around basins, and not just crater basins. So that's a hole. A crater is a hole, but it's not really a structural basin as the way I'm talking about it here. So we're talking about annular spaces around giant basins. That would be Utopia that's buried. That would be Hellas in this case, or Isidis, those kinds of things. So instantaneous accommodation space, and you can have an expectation about what will be filling that space. So immediately you have giant mega breccias being shut off into the basin. You've had these fanglomerates if you have any kind of aqueous activity, so you can kind of go through the geology and see what's going to happen there. Okay, so don't go through all of this here, but the regional setting is, here we have Hadriacus Palus. Here's kind of the global map that you guys may or may not have picked up out there. Wrapped around a globe, but it's early Noachian. It's an extensional basin. Has Noachian to early Hesperian basin fill, late Hesperian basin exhumation. In there's basement material that's been upthrown, sedimentary rocks, volcanic rocks, impact rocks. There's lots of things going on here. Diverse provenance. We have two different channel systems that I'll go over here in a second. Lots of different things to see in this area, and it's all exposed. It's all exhumed. It's all there for us to look at and to access. One of the points here, too, is that this is totally normal, in my opinion anyway. This basin is not special at all. It's intercrater plains. It's typical highlands. In this case, what makes it special is that it's exhumed. You can see parts of it. It's not the only one that's out there. There are several other basins that exist in and around Hellas in particular, but other places on Mars that are exhumed, and you can see these kinds of sequences. Okay, one of the important parts about this too is that anything we see here has broad application to Mars. Tectonics in particular, if we see these materials, we see these breccias, we see how they're interfering with other kind of basin deposits, that gives us a really good indication about how the tectonics are working. And that's one thing that I've appreciated all the different talks, but one thing that we can go visit a structure, but when we actually see the materials that are being shed off of that structure, that gives us an idea about how that's being active. And that's really, really important for us to understand how Mars is working, how the crust of Mars is working. Okay, so here's the exploration zone map. Landing site right here in this flat area. Okay, we have two different valley systems that are coming from the north. It's Napa Vallis and Willaga Vallis coming off from the east. These are shedding basically early Noachian to late Noachian typical crater highlands from the north. And off to the east is coming from early Noachian Hellas massifs, Hesperian volcanic assemblages, as well as volcanics from Hadriacus mons. Okay, so basically flat. It's a rock-free surface. Here's kind of a little shot of this right here. It's basically a little bit dusty, not a whole lot of sand deposits, basically flat. And so these massif-bound intercrater basins, you see all of them popping up around here. Okay, they don't look like much now. This is kind of stretched to even emphasize them, but they don't look like kind of massifs, but they're really, really old. This is an old event, Hellas is. And so uplifted blocks that are related to Hellas, there's a question mark there. That's what I think they are, or at least most of them are. Have they been affected by any kind of post-Hellas impacts? You can kind of make out what might be a circle around here. And so we have massifs that are being thrown up by Hellas. You have post-impact on top of that. Some of them might be old ancient volcanoes. We've kind of had evidence of that in different places in the highlands, so lots going on here. Okay, so we have science ROIs. I'm going to talk about, there's a lot, everybody said, there's lots that you can pick out here. What I'm going to point out is this channel convergence where you have these two, Napo and Walaga Vallis coming together. I'm going to point out some of the massifs, basin highland contact, the cavity strata to me. So in here, this is Hadriacus palus, and then there's these cavity, basically depressions that are right down there at the bottom. That's the exhumed part of the basin sequence. And so Hadriacus cavity, this cavity strata is to me one of the most important parts of this region. And then I'll talk about a little bit of crater-related deposits. And then for resources, we have some phyllosilicates and we have building materials. So like I said, going to get it out there, resource limited, but here I want to make the point that here science is driving something. Do we need to kind of figure out a way to make other observations? Okay, so channel convergence is about 33 kilometers from the kind of landing site or the field center. Napo Vallis right here, Walaga Vallis down here. What you can see immediately is that there's these sinuous ridges. So this is a channel that has come down at some point in the past into this basin. You can see kind of the edge of the palus right here. We've dated these surfaces. They are at 3.38 for what you want to give that. This is kind of a relative dating for us, 3.38 plus or minus 0.08. So, you know, kind of latest Hesperian type of thing. So these raised ridges is channel deposits being exhumed and then another channel deposit that's abutting it and moving around it. Same thing's happening down at Walaga Vallis. Here you can actually see that the second event is actually moving over this kind of raised ridge and actually going down into part of the basin. Really interesting. So inverted and abutted channels, what are the fluvial dynamics here? What are the processes of inversion? Can we correlate the timing between these two channel systems? What is going on? Can we see provenance differences between what's coming from the north and what's coming off from the east? I think that's really interesting. When we start going down into the cavity strata, can we see those changes in the cavity strata as well? Because presumably these are feeding at least the uppermost part of the cavity deposits. Can we kind of see when these are each going off within the cavity strata? Two different source terrains. Let's see. The palus scarp, so this has been eroded back. Another thing to point out here with these kind of yellow arrows is that this surface has been stripped back. This, you know, on the order of 5 or 6 meters or so along this kind of blue line. And what's exposing that is kind of this little bit rougher surface, but you also have these really kind of curvilinear ridges that are moving through here. And we're interpreting these to be kind of little fractures that have been filled, so cemented veins. Okay. So massifs, 1, 2, 3, 4, 5. There's many places that we can go within this kind of exploration zone that are talking about these massifs. In this case, this is the one that is highlighted up here. This is on the south side of that exposed cavity deposit. And here we have, it's kind of hard to see, but this is the top, this is the bottom, 20 degrees or so. You have kind of the stratified deposits that are sitting on top. And down below, we don't have anything that we can see as far as stratification anymore. This is more like massive material. So is this old regolith? Is this crystalline rock? What is this stuff? It is really, really fractured. It has been faulted. It is fractured running all different ways through it. Really, really interesting. So this would be one datable unit if we're talking about datable units. Got it, thanks. Okay, basin highland contact. We like margins of things. So we like where things overlap. So let's talk about where the palus then goes and sits on top of this kind of older material. Here we have the same surface as 3.38. Here we have a resurfacing age on the adjacent unit that is subjacent to this kind of palus surface. That's 3.39. And so basically what we're seeing is a 4.06 crater terrain that is being shed and eroded at 3.39. This correlates with what is going on down here. So we have crater terrains and being eroded and deposited into this basin at the same time. So impact craters, we have primary craters, we have secondary craters, we have these giant basin kind of structures that we can look at. So lots going on there. Okay, cavity strata. This is the most important thing to me. Maybe spend a little bit extra time on this if I have it. So light dark stratification. This is what all of these deposits look like. Lots of colluvium sits on this. It's light dark, light dark. A lot of colluvium coming off the side. The colluvium itself looks like it has been placed and then been stripped back. Maybe some of these cavity kind of troughs have moved back with it. And so you have a colluvial history there. You got an aeolian history here. You got all of these kinds of deposits. This is really nice. So top to bottom, sometimes it's a little bit hard to see. Aeolian materials, colluvial materials, it's kind of mantle materials. One of the most important things, and one of the reasons we started studying this was, there are two things. One was these things that look like columnar joints to us anyway. Okay, this is in a very repeatable section, kind of halfway up these cavity strata. So this is the side of them, kind of looking into the side. This is the top of that same bed. Okay. Another datable unit. Those are volcanics. Cavity strata. Here we have channels. There's lots of channels that are going through this deposit. Again, this is the second part of the reason we're studying this area. This, to us, is also occurring in kind of a repeatable area above those columnar joints. Here they are here. There's one, a couple down here. These look like channel cross sections to me. Okay, there's no way for us to figure out how to get these at impact craters or that kind of thing. We've done some studies, done some measurements on it. All of these are sitting within one certain section. They jump from one trough into another. So this is what we're interpreting to be something that is a cross section of a channel system. We also have channels on the floor of some of these eroded stratal forms. We have things that are coming out the side that are inverted. Lots of different channels there. Okay, moving on to, so that's out of the stratal deposits. I mean, I can go on and on about all the different things that we see within this kind of cavity deposit. There's lots of different things there. Basically going from all the way from the massif to the megabreccias and everything that are being shed off of it, all the way up through the sediments. Those sediments might be the impact craters, volcanics, the channel deposits, all that kind of stuff. So this is moving out of the cavity off to the west in the exploration zone, looking at some of these impact craters. There's several impact craters that reside within the exploration zone. One of them has a nice big central peak. This is also a datable surface. We can compare this to all the different massifs that we see, as well as the one that's uplifted and being shed off into the basin. We see these kinds of layered deposits here that have been eroded out, and then you have lobate deposits that are moving off in kind of a fan that comes off on the western side of this crater. So this is something that's kind of on the margin. All of these things are points of comparison to other areas within the exploration zone as well as places outside the exploration zone. Okay, so now the bad news. To me, this whole geologic story is really, really interesting, and we get to a place where it's like, yeah, well, there's nothing much here for us. CRISM doesn't show much for us. What we do see is phyllosilicates. You know, I'm not a spectroscopist, so when somebody comes to me, Christopher Edwards was nice enough to help me with some of this and say, you know, we see some phyllosilicates. They occur in a couple different places here. We see a background of mafics everywhere. We can trace the phyllosilicates that we see here to kind of a weak signature along the Pallas margin, but not a whole lot there. Is it not there? Are we just not seeing it? And that kind of thing. So we have another image that we requested for March 2020 when this area was at one time a minor consideration for March 2020. But here we have this kind of this area right here. So nothing's being shown in CRISM. We expect certain things when we have these environments. We're not seeing them. You know, what does that mean? What we might have here are building materials. One thing in particular are these excavating out these the channel deposits. You'll be able to see the different kinds of grain sizes and that sort of thing. Okay, so now that I'm lurking, gotcha, 2. All right. Here's the data coverage we have. CTX basically complete. We have this data. This is what we're mapping on. We're constructing a 1 to 50,000 scale geologic map of that cavity deposit right now. High rise about 6%. We have stereo pairs. CRISM about 6% or so. And so these are kind of the several ones that we have around our area, which is in the cavity. We can go through this. I mean, I appreciate what the rubric is trying to do. I have a hard time filling out, so it kind of just peters out towards the end there. Sorry about that. And so, but willing to talk about it for sure. So anything, I think I might be the only one that's saying this, is that, you know what, I don't think I need any more for this project. And so I kind of feel bad about that because everybody else is asking for it. We can definitely use it if you want to shoot some high-rise data, but we don't need it for science. What we do need is some CRISM data, especially along the edge, to be able to see if we can, tease anything out about this region. Otherwise, it's not going to be something that's going to be successful for, further consideration. But the type locality, I think, is really good, kind of an exhumed basin deposit. So, parting words: non-crater tectonic basins, optimal exploration zones. Hadriacus Palus might be resource limited, and I think is a good type example to ascertain what data could bring the resources more into focus. Okay.
Okay, and we thank you for being discriminating about your data requests. Bryony. I'll get it right one day. Bryony Horgan is our next one up. Your site is on the map? Mawrth Vallis. And we'll hear more about that here. Go ahead.
Great. All right, thank you very much. So we'll go out with a bang with Mawrth Vallis. So Mawrth Vallis, in my opinion, satisfies every single major criteria with flying colors. So let's see how that happens. As we're saying in the title, we have lots of habitable Noachian environments and incredibly abundant resources in this one location, which you can again see here on the map. Okay, so here are, right now we have two different exploration zones. They're actually really similar in terms of the science. Really, it's just because of the two different landing sites. So landing site number 2 down here is located where it is, because this is basically the location of the Mars Science Laboratory and Mars 2020 ellipses. So it's a very well understood, very well characterized location, very safe. However, I think this site up here actually gives us better access to science, and it's also, I think, a better landing site for these purposes, as we'll see. But you can see the major topographic features here, lots of diversity. You can even see just from the scale. Here you can see Oyama Crater, you can see the Mawrth Vallis outflow channel, and you can see the northern plains and the dichotomy boundary. So lots and lots going on here. Looking at albedo and looking at the actual site itself. So here, again, our two landing sites. You can see this northern one really captures a lot more of our science ROIs. The southern one really just gives us one extra that I'm not really sure enhances the science quite so much. But here you can see here's our landing site and a habitation zone. It's on this regional mafic unit, excellent resource for basaltic sand and all those things. We also have lots and lots of resources. I would say resources fill of anywhere from 1/4 to 1/3 of the entire exploration zone. And we have lots and lots of science ROIs, both up on the plateau, inside Oyama Crater, inside Mawrth Vallis itself, and out in the northern plains. Okay, so I'll go through this really briefly. So Mawrth Vallis, why does it have value as an exploration zone for human exploration? First off, it's a mineralogically extremely diverse site, recording a sequence of ancient habitable environments. We can sample both in-place ancient altered Noachian deposits, things that formed in place, and then watch them as they were transported into a basin and deposited via fluvial processes. It's a rare example to be able to do that. It's also an extremely ancient place. It's one of the places where we can really analyze ancient Mars, potentially the entire Noachian in this one location. We have lots of different astrobiological targets, really good motivation for what kind. We actually think it might be able to even think about what kind of microbial ecology we might have at this site based on the mineralogy. And of course, we have access to a Noachian outflow channel, the dichotomy boundary, and the northern plains all in this one site. And then finally, sort of the reason that Mawrth is so exciting in particular for this is that it has incredibly abundant resources. Okay, so putting Mawrth in a global context, so Mawrth Vallis, the reason it's exciting is because it's a giant stack of clay deposits, incredibly abundant clays. But that giant stack is just, that we see in our exploration zone, is just one exposure of a much, much larger deposit. Here, this is where this location is on this map, but we see, people have seen exposures of that same clay unit extending almost 1,000 kilometers into Arabia Terra. So this is truly a regional unit that we'd be interrogating and trying to understand. Looking at the stratigraphy, we have over 200 meters in places of layered clay deposits, and it's generally divided into two major sections. We have the lower, approaching 150 meter thick stack of iron magnesium smectite clays, with lots of other stuff interbedded. There are ancient cratered surfaces, there are sulfates, there's all kinds of other stuff in here. And so this is really a built up over time section of clays. That's what we're looking at. On top of that is capped with this interesting unit. It's dominated by aluminum clays and other aluminous phases, as well as lots of other interesting stuff as well. On top of that, we see evidence for lots of fluvial dissection, in the late Noachian at that terminal unit. And on top of that, the reason we see it is because it's been protected by this overlying mafic capping unit on top, which is now being eroded back. But in total, we're seeing 200 meters of extremely clay-rich sediments at this site. So how do you form a 200-meter thick stack of incredibly abundant clays? Well, one misconception about Mawrth is that you can form it by basically putting down your stack of sediments and then leaching them with one big leaching event. It turns out that's very difficult to do. This thing is about an order of magnitude thicker than typical leaching profiles on Earth. Instead, we think it's more likely that the stack was built up over time through concurrent weathering and sedimentation. Basically lay down a layer of sediments, weather it to form a soil, and do that ad infinitum over and over. I've been doing a lot of analog work in the past couple years looking at sites like this is Eastern Oregon. This is a giant paleosol sequence. With every layer in here is a different soil recording an ancient paleosurface in an ancient environment. And so what's really great about these kinds of sequences is that they tell us not just about how the soils and mineralogy and all that evolved over time, they tell us about how the climate evolved over time. And these things are great climate records. And so what's really exciting about Mawrth Vallis is that 200-meter thick stack, we think, spans the entire Noachian. And so that might provide us with a climate record extending throughout the Noachian of Mars. Okay. I just want to point out that every unit in here that we see represents a paleosurface, which could contain streams, ponds, all these things, and it's a very habitable environment. Okay, rubric I'm not going to dwell on. Lots of dots. I filled out a lot of these things over the past year. Okay, getting to our science ROIs. So our first science ROI is basically the location of the previous rover ellipses, and this is a fantastic place to interrogate this sequence of potential ancient paleosol deposits. We see lots of mineral diversity. This is a CRISM parameter map showing mainly the aluminous unit on top, all this blue stuff. We see the underlying iron magnesium smectites. But then it's the details of the mineralogy that get really interesting, because we don't just see the smectites. We also see different kinds of acid sulfates, localized exposures of them, jarosite, alunite. We also see evidence for reduced iron-bearing alteration phases. So not, mafic pyroxenes and things, but actual reduced iron-bearing clays and stuff like that. And so that implies the close association between ferrous reduced alteration phases and oxidized alteration phases like these acid sulfates imply a redox gradient, local redox gradients of iron and sulfur. And that's really exciting because that's exactly the kind of gradient that life would like to exploit for metabolism. And so here's a place where we can say, we think the kinds of microbes we'd be looking for would be just like those that undergo iron and sulfur reduction and oxidation on Earth that actually facilitate that process. And what's more exciting is that these reducing environments indicated by these reduced iron-bearing minerals would be fantastic sites of organic preservation. In fact, the kind of assemblage we're seeing here is the same kind of assemblage we get in wetlands on Earth. So that's the kind of environment we might be talking about here. Okay, so looking at the ROI, it's been well mapped. Damon Loiseau et al. Have a great new paper that just came out in press, providing this nice map, which has just lumped everything into the aluminum and iron-bearing units. And so the main target here would be the clays, trying to establish what's going on with that sequence, doing chemical and isotopic profiles to evaluate the climate significance of those soils. We'd also be targeting those reduced iron-bearing alteration minerals to look for preserved organics. And there's also other stuff going on here as well. There's all these inverted valley networks, these yellow lines in here. There's all kinds of interesting fractures that exhibit potential evidence for post-depositional alteration. And there's some exposures of this regional mafic capping unit as well. Okay, jumping to our next ROI, this is in Oyama Crater. So we were just looking up here on the plateau at the layered deposits. This is sort of a source environment where we have active alteration going on. Now let's let that stuff wash down into a basin and get sorted, potentially by grain size, hopefully, and look at what it looks like afterward. That's what we see in Oyama Crater, is sort of this basin sequence. Of course, this is part of a much larger fluvial dissection that happened toward the late Noachian. Here you can see a map of all the different inverted valleys and valley networks that we see at this site. And so we're interrogating this time period. When we look in Oyama, what we see are these very finely layered clay-rich sediments that we're interpreting as probably alluvial, potentially lacustrine as well. But you can see how different they look compared to the same kind of clays up on the plateau. There's all this fine layering. Here it's very muted, very hard to pick out. So it's clearly a different depositional process. What's also exciting about this ROI is that we have a fantastic datable lava flow. And when I say datable, I don't just mean through radioisotope dating. We can actually also link it to the cratering chronology, the global cratering chronology, and help us understand the global ages of things on Mars. We also have a wrinkle ridge that passes through the lavas down here, which is part of a regional wrinkle ridge network. So that could help us understand those tectonic processes. Jumping just to the north, we can see our next ROI. This is another datable, probably volcanic surface. This is part of this regional mafic capping unit. Here you can see it's also fairly high thermal inertia, just like the lavas on the floor. Here it is blown up with albedo here in CTX. And so this is, it's a cratered, well-dated surface. It's pyroxene bearing. It covers a huge part of the region. It's sort of irrespective of topography. We think it's probably a pyroclastic deposit, which would be nicely datable. You can see this is also the base for this northern landing site. It's a nice basaltic base, bedrock, very smooth. It would make a fantastic habitation zone and landing site. Moving forward to the next science ROI, going down into Mawrth Vallis itself, this is totally accessible, slopes below 10 degrees. But we can actually explore the outflow channel and explore the interesting features. There's all kinds of interesting sulfates and other mineralogy down here. Moving up the outflow channel, we can actually start to see interesting crust exposed by the incision of the channel itself. So here we're seeing these what looks like mega blocks of some sort in the base of the outflow channel. We're not sure what they are. They could be deep crust. They could be megabreccia. We're not sure, but they would be an interesting target. And then finally, getting out of the outflow channel, emerging into the northern plains. So pulling a Mark Watney and using Mawrth Vallis as a way to get from the highlands into the lowlands. And here we can actually sample and interrogate the northern plains fill material up here, which is late Hesperian in age. Okay, next we have excellent impact processes at this site. Here's a nice large, relatively recent impact crater with a large ejecta blanket that we could interrogate. And then finally, here's the example, the one major science site that we can get to with that southern landing site. It's sort of more mineral diversity in the southern flanks of Mawrth Vallis, sulfates, clays, potentially some lacustrine clays. So it's interesting, but again, I think that northern landing site is a better target. And then finally, there's a really interesting potential mud volcano on the far western side of the exploration zone. It's this big dome you can see here, which when you look in, it has this circular pit and this interesting lobate form apparently flowing out of it. So that might be an interesting target to interrogate sediment sourced from depth. Okay, so that's the science ROIs. You can see there's a lot of diversity in addition to looking at ancient sediments from ancient Mars. We can also just look at a lot of different processes, volcanic, impacts, fluvial with the outflow channel and all of our fluvial deposits in Oyama. But the other really major value for Mawrth is the resources. So as I said, we're dealing with this huge regional scale clay-rich deposit. And when I say clay-rich, I really mean it. Both visible near-infrared and mid-infrared spectral modeling have implied abundances in excess of 50 weight% clays. And when you add in other hydrated phases like ferrihydrite, we're talking about something in excess of 75 weight% hydrated minerals, especially in that lower iron magnesium unit. And so when you actually work out how much water that means, and this is confirmed both with spectral modeling in the near-infrared as well with, and it's consistent with laboratory investigations of these kinds of materials, we're talking about anything from 7 to 9 weight% water in these clays. And so when you actually calculate how much water that is, if we look at the entire exploration zone and the whole deposit 200 meters thick, we're talking about 100 billion metric tons of water. If you're just talking about the upper centimeter of those deposits, we're talking about 10 million metric tons of water. So the area you would need to excavate 100 metric tons of water at 1 centimeter depth, so scraping the surface, is a square about 175 meters on a side. If you go down to 10 centimeters, it's 50 meters on a side. So it's really an incredible water resource. These clays, as Jack mentioned earlier, kaolinite, which we see here, is an excellent source of aluminum. These iron magnesium clays, as well as the sulfides that we infer are present here, would be excellent sources of iron. So Mawrth is just an incredible resource for human exploration. Okay, so getting to the data, Mawrth has great coverage already. There isn't a lot we need to make the science case here. I would say the one thing we do need is more high-rise and chrism over that northern landing site to really look at slopes, roughness, all of that stuff. So I think that's the really big thing. Okay, and so I'll just leave this up for you to look at, but thank you for your attention. Great.
If you're a speaker. Oh, you're going to put the email up? That'd be great. Oh. We missed? Oh, no. I thought he was escaping. No. Any question over there? Microphone. Oh.
Hello, Jack Holt from University of Texas, Austin. This is a comment, or maybe more of a comment / question for the first talk, and then some earlier ones today where there's geomorphic evidence for ice in the subsurface. So there's a crater with some concentric crater fill, indicating the presence of ice, and more chrism and more high-rise is not going to tell you the answer to that question. And like a lot of the earlier talks, this features that people showed are just below the resolution of Sherrod, as Jeff Plout mentioned earlier today, and far below the resolution of Marsus. But with a next generation orbiting radar, we could get an order of magnitude improvement on the resolution, both vertical and horizontal, and we could see if there's water ice and features like that. So I would like to stress that we could do a lot better with radar designed just to look at shallow ice deposits.
Yeah,
So-
agreed.
So actually, I'm going to ask an ignorant question first, which is the best kind, which is, I mean, a bunch of the talks today and yesterday have referred to hydrated minerals, so particularly the sulfates, and they have quite a wide range in the amount of water that they think they might hold. So I would like someone in the audience, because I imagine I'm not the only one that doesn't know, but might be, can chrism in a certain mode answer that question, or what future data would be needed to be able to say? Because it makes a big decision on how much depth do you have to excavate. What do we need to know what the actual amount of water is in these different hydrated minerals?
So if you know what mineral is there, you can use chrism to help constrain that by looking at the water bands, especially the 3 micron water band. The 7 to 9 weight percent amount of water that we cite for Mawrth is based on, I think that's Ralph Milliken's work, looking at those bands and trying to associate them with a specific mineral abundance based on lab data. So with enough work, you should be able to use chrism to at least constrain it.
So there's another sort of important point here, I think, is number one, clays and sulfates have sort of a different story with regard to water. Obviously, that's come out in some of the talks. And not all clays are created equal. There are some subtleties in terms of crystal chemistry, things that we can tell with chrism that affect greatly whether those clays would be considered great resources or not. For example, smectite versus not smectite, mixed layering, those things. So for example, smectite has accessible water in the interlayer sites that can be liberated at low temperatures around, say, 150 C, similar to sulfates. Grain size of the clays and sulfates affects how easily that water is liberated. Secondly, hydroxyl within the phyllosilicates is liberated at higher temperatures. For dioctahedral clays, that'll be a lower temperature than trioctahedral clays. So things that are magnesium rich, that means you have to heat it to maybe 7, 8, 900 degrees C potentially, versus dioctahedral ones which you only heat to 400, 4 something. So we have 20 years to think about that. So, but those are the kinds of things that one might keep in your mind when you compare different mineral resource ISRU candidates.
And I'll just kind of add to that it really, I think abundance makes a big difference too, because you have to think about how much material you have to heat up to get your water out. If you have a very high abundance clay or sulfate or whatever, you don't have to mine and heat as much material to get the same amount of water. So it's much more energy efficient. So abundance really matters in this case.
Hi, Briani. The comment, I'm really impressed with the diversity that Mawrth offers on that 100-kilometer scale. And I don't want this to sound the wrong way, but it adds, to, in my mind, it adds tremendously to the little section that we would be looking at with either MSL or M20, where you're just in that one little zone. But here, the possibility of going down into Oyama and looking at older things, in addition going away towards the Nowakian and be able to put that stack into a broader perspective, to me, adds tremendously to the appeal over what we would have seen from that smaller area. And then the final comment is we looked at 2 landing sites to the north in that capping unit for MSL. And I'm trying to remember why we abandoned them, but I'll try to burrow in and show you what we found.
Well, if it was in the capping unit, they wouldn't be as interesting, so.
Yeah. But we did get a bunch of coverage, and I think we might have gotten a dem or 2 to look at the small-scale slopes and stuff.
Okay, that'd be great to see.
Okay, back first and then middle.
Okay, Rob Mueller, KSC. So when you say clays and 8 to 9%, that's very interesting from a mining resources point of view. And then one of the criteria is automation of mining resources. Well, I'm building mining robots. Can you tell me what the physical form of the clay is? It's a little confusing to me.
Yeah.
Because I get different definitions of clays from different people, and then a terrestrial intuition of a clay is probably not the planetary correct intuition. So can you just clarify from a mining point of view, how would you mine a clay?
That's a really good question. So the clays we're talking about here, we're talking about clay minerals, which is the word everybody should use, and I always forget, and everybody does too. But clay, when you're talking about clay on Earth, you mean a grain size, right? But here we do mean the minerals themselves. This stuff is now clay stone. I mean, we see impacts into it. It's rock at this point. I think a really important question that I don't know if we have the information to answer yet or not is what form the surface immediate, that first centimeter of the surface is in, if that's regolith or not. One of the reasons we see these lovely exposures of clays here is because it's totally windswept. This whole area is completely dust-free. It's being blasted by wind. So does that leave behind, cobble-sized broken up clay? I don't know. And I think that's a bigger question for all of these hydrated mineral deposits is what is that very upper surface layer like? Can you scoop? I don't know.
So what do I need to do to find that answer? And what do I need to request from the organizing committee?
That's a good question. I don't really, because we're talking about, how do you figure out if something is cobbles versus, solid? I don't know if thermal inertia could get at that. There are other geologists in the room who could.
Okay.
Rover.
Okay, I'm afraid that I'm going to be a dissenting voice over the last 2 days that I've been listening here. What I hear is everyone praising their little bit of Mars, and what I get away with is Mars is an interesting place. I already knew that, or I wouldn't be here. And, there are lots of things we would like to explore. I also understood that from years before. But what I also hear is all these presentations that I have, if I look at the differences in height, we'll say, oh, this is a very interesting place. And then I look at it and I think, diving 2,000 meters into the crater, how do I get up? Yeah, it's all very interesting, but how much practicality, and not yours, just in general, is there with all the things that are presented? I understand everyone's wish to get to their specific part of Mars. I understand that. But how practical is it what we are presenting here?
I can just say for Mawrth, I just briefly looked at the MOLA slope maps, and there are many, many locations along Oyama Crater rim and the Mawrth Vallis flanks where the slope is well below 10 degrees, which I think is the stated limit for traversability. Now, we still have to look at the detailed traversability. What are the boulders like? What are the local slopes? But that's something that has to be done with much more detailed investigation.
Yeah, and to be clear, when we set up the workshop, we did specifically, in the guidance to the presenters, they weren't expected to do detailed traverse maps. That's something that will come as part of the future analyses of these E's, to show that they can, with reasonable slopes and trafficability, get between all the ROIs that they've picked.
Oh, I had a little bit to say about that. I think one important thing to remember, just to consider, is that, there are lots of different spatial scales you're talking about. So, if you're looking at the whole EZ, Obviously, there could be some rough areas, some smoother areas. But, at least with mine, again, sorry, this is kind of going against the whole, talking about the whole planet, but obviously with my particular area that I looked at. When you get down to the scale, and I think the particular constraint was like, for the rover, it was like 30 degrees slope and a path that's 5 times wider than the width of the vehicle, something like that. If somebody correct me if that's wrong. But I think within my area, that was generally met, at least getting up to the features themselves. Obviously, if you're going down into steep craters, that could be a little bit of an issue. But just when you're thinking about just any given place on Mars, maybe even just statistically speaking, I think that kind of parameter might be met more than you would think, just looking, doing a visual inspection.
Stan?
So, thanks, Artemis. Yeah, we do need to be thinking about traffic abilities. Has anyone in this room ever been to Meteor Crater, Arizona? I figured. When you look down into that, did you think, I'm gonna drive my car down that? That looks really easy. So, no, I had my first look at it when I was a rover driver in Desert Rats 2010 out north of Flagstaff there. And even with practice driving that rover, which is quite agile compared to a car, you look down from the rim of Meteor Crater and you go, no way, not driving down that. So I agree, Ben, this is early days, but just remember, I've heard mention of, 10% grades or 10 degrees. A 9% grade sign on a road when you're driving, you go, oh my God. And if you're driving a truck, it's like, I think we better find another way to do this. So do be thinking, slopes that seem moderate from if you drew it on a piece of paper, once you're in the driver's seat of a vehicle, they might start looking a little more daunting, especially if it's covered with rocks or sediments that might slide. Anyway, thank you.
Thank you, Stan. I didn't have a chance to go into detail about the difference between ancient craters and young craters. Young craters, you're going to go to the ejecta, readily available, but probably not go in. They're usually going to be smaller scale, 1 kilometer like Meteor Crater. Ancient craters, basins such as, is it Endurance, or Endeavor, where opportunity is, you can drive into a little bit easier due to the back wasting of the rim.
Yeah, I had something else to say there. Is that so reporting any kind of, whether it's me or anybody else that might be reporting any kind of degrees, and because our responsibility was not to say, we're going to drive here. I mean, I'm just saying that this is the context, okay? So something at the bottom of this one slope, even though it's something that, might seem small to walk on, is not something that's small to drive on. So we're just establishing context, and that's what I kind of thought that this whole thing was, is to say that, look, in the end, science is not going to be the driver for this, okay? Safety is going to be the driver, okay? And science is going to take a back seat, and as much as that offends us, I think that that's a fact, at least it's a fact to me.
You don't get any science if you crash the rover.
Right, okay. So safety wins the day. And so we could either say, this is what the safety parameters are, and make a mask on all of Mars that we can do with these basic kind of nominal criteria and say, these are the only places we can go, and then start to look at those, or we can kind of go iteratively and say, these are the safety places. What's that?
I said, you have 100 kilometers, for Christ's sake. You can find a place to drive around safely.
Right, okay. The iterative process is to say that here's where we want to go, here are the safety concerns, and go back and forth. Is that correct or not correct? Am I misinterpreting?
Let me add to this. The vision of the HSO SAG that Paul talked about at the opening of the meeting, and we've heard some comments from Jake at the back, is that the exploration that will happen is a combination of robotic and humans and the robotic-human partnership. And it doesn't necessarily mean that every bit of work that is envisioned by the scientists and visionaries that are present in the room means that a human has to have their hands directly on it. It may be an appropriate thing to do to send a robotic asset down into a steep crater that's too deep to drive on. So we need to be patient and hear what the reasons for interest in these various kinds of things are, and then let the implementation flow from that.
Okay. Who's first? Okay.
Yeah, Jake Bleacher at Goddard Space Flight Center. Jim, I had a question for you. Your presentation was talking about tying into kind of more of a global understanding for the planet and talking about these stacks of materials. And I think Bryony was getting at that as well, and that her sediments may have been deposited over long periods of time with multiple stages of erosion and soil development. You right away said this is resource limited but science rich. Do you think that the strategy you're presenting could be applied in different places maybe, and you might be able to find locations that could be somewhat more resource rich that might fit with your concept?
Yeah, I think so. And so in the abstract we said this is an example. This is kind of a type of what we want to see. This is, to me, what would give the best bearing on tectonics. I think is an issue for Mars, is that everything's buried, everything is covered up, and so to be able to find a place where we at least think with reasonable plausibility that this is something that's uplifted, this is crystalline rock, or this is really ancient rock. This is not the only place in Hadrian's Palace. There are other places that are like this. Vallis is one of these places. Along the Highland-Lowland boundary is another place. And so, yes, there are other places that are like this. This is kind of an example of look for these things. This seems to be really interesting. Tectonics is important, and we haven't really gotten to a place where with the size of this exploration zone, we have a lot of places to go, and I think that there are places that we can go to see what these faults are doing, and that would have a big implication on what we understand the crust of Mars is doing, and we haven't done that yet. So yeah, I think that we can apply it to other places for sure.
Hello. Yeah, so I do kind of have a little bit of a comment, mostly for, I'm sorry, I forgot your name, for your presentation. Yeah. Jim, sorry. So like NASA works for the people of the United States, and like this whole conference, one really big part of it, especially in terms of science, is to try and determine whether there is life on Mars. And you didn't mention it at all in your talk, which is, I mean, practical probably for you because you're a geologist, right? But you have to be able to justify where we're going to not just the scientific community, but to common people as well. And if you tell them that we're going to spend all this money to go to a spot that just has geological science, it's just not very convincing. Like, I'm just wondering what your take on that is.
Well, I would say that if we go to a spot that only has astrobiology, then it's maybe not as interesting to everybody else as well, right?
But
So
people who've presented a nice even both astrobiology and geology, and they've kind of combined them both.
I'm just throwing one site out there. I think that this one site has the ability to be able to have those kinds of environments. We can predict those kinds of environments. The competition doesn't give us the ability to say that they are there, they might be there, we can't see it. So our job is to set the context. Like I said before, our job is to set the context. And one of the things I've been thinking about over, kind of running up to this meeting and then also being at this meeting is that Mars 2020, for example, seems to be very driven by astrobiology. And that's important, as you state. It's something that we want to get after. Once we choose a place and we go there and it doesn't pan out as far as astrobiology, it still shows you environments where life could be. What does that leave us? Okay, and so do we do that same exercise again and then try to take another crack at it? I'm not saying yes or no. I'm not saying right or wrong. I'm just saying we should be cognizant of the processes leading us to any one place, not be biased by the whole process, and to, again, take a step back and look at context, let everything play out, and kind of feed the iterative process.
Yeah, and I'm going to add to that. When we had the science, the HSO SAGs, there were the multiple science disciplines, and they weren't prioritized. And it's perfectly acceptable for someone to come to this first meeting and present just a certain aspect of that science. And then one of the good things about the fact we have such a diverse group of people in the audience is if you think something isn't covered, but you could help, then you can get in contact with the speaker. But every speaker doesn't have to cover everything that's covered in the rubric.
So just a question for ISRU people and a comment. Robin and I wrote a paper about thermal inertia of clay, so she'll say something about that. But I wanted to ask, when it comes to mining materials, it made sense to me in thinking about this presentation that materials, even if they're really hydrated, if they exist in bedrock, as an astronaut, you probably don't want to be banging around on bedrock trying to mine stuff out. So things you can find either in debris flows or ejecta might be interesting, although ejecta may be devolatilized during the impact process. Maybe it's just something to think about. The timescales involved may mean that. So in terms of the clays at Mawrth Vallis, I think that something, a comparable type of rock might be some of the soft ones with low grind energies that you see in the Columbia Hills, things like Clovis and stuff like that. And there are some reasons I think that. We can talk about it later if you want to. So I would be interested in knowing in the future, maybe not even, maybe now, maybe in the future, what are physically good targets for ISRU. Would you want things that have been disaggregated through natural processes or not? And Robin knows all about the grain sizes and thermal inertia too.
Robin Ferguson, USGS. I wanted to comment a little bit on the question about clays. And I think the question was, what is the physical nature of clays and how can I find out? And this is a broader comment that I have than just thermal inertia. I think as we're doing all of this, we need to keep in mind the limitations of the data that we have. There's only so much you can do with remotely sensed data. And trying to absolutely understand what the physical nature of a material is, I think is one of those things that we're very limited by the data. And I have my own ideas about what the nature of the phyllosilicates are at Mawrth Vallis. And a lot of that's just based on intuition, going out to field sites and seeing the geology and thinking about what makes sense within once you integrate many of the data sets that we have, not just looking at a single data set like thermal inertia, but integrating that with the albedo and high-rise imagery and what do we see with CRISM and what do we see with test mineralogy data as well. So I think as we're going through all of this, we do have some significant limitations when we're just looking at remote sensing data and pushing the limits of what we can understand and interpret, but kind of, keeping in mind that that's indeed what we're doing.
So I think analog studies, I think, are a really important aspect of this, and we have some ideas for analogs for some of these sites, but some of them still need that work.
Yeah, so I was just going to go to back to the astrobiology point for a second. I think maybe sort of, because I'm also a geologist and not a biologist, so I kind of have this viewpoint from sort of the other side of the fence. I think, obviously one of the very, from the very beginning of Mars exploration or really space exploration at all, has been, searching for other places where life might exist. And a lot of that has to do with looking for water and these hydrated minerals and other potential resources. But I think maybe some of the issue springs out of the fact that, the astrobiology has been so much in the public eye, especially more so lately with all these publications of discoveries of this and that. But again, what I was saying in my talk, I think the best sort of way forward, and also Ben was saying this, is to really equally emphasize all these different aspects. And I think maybe the reason why both of us, Jim and I, did sort of emphasize the geologic aspect more, or whoever else is doing that, is because we want to make sure that that's sort of there's even coverage, even attention given to each of these aspects of Mars science, because they really are equally important in different ways for figuring out basic fundamental problems about Mars itself. So.
Okay, so last two at the back.
Okay, so I wanted to echo what Dave Beatty's comment and just reiterate regarding some of this conversation is I think that it's really important that we understand here what we are doing is outlining what we want as a science community, what we want as an ISRU community, and drive the implementation as best we can. Of course, there's going to be now a push and pull, a conversation to be had with the implementation side that will respond and say, no, you can't do that, or yeah, you can do that. But one of the things, the conversations that we had were with the EDL people was they said, yeah, we could go higher elevations if you guys really feel like that's important. That's going to take a cost. I mean, you're going to cost more mass. So there's push and pull to be had, and it comes from, if the clays are hard to dig out, then we're going to have to bring more mass to dig them out, or and we'll have to treat each of those situations separately. So I think it's important to realize that this is a conversation. We go back and forth, and it's really important that we outline what we want, whether it's astrobiology or not astrobiology.
I think it was a comment, not a question.
Oh, okay. All right. I'm Leslie Gertsch, Missouri University of Science and Technology, and I'm a mining engineer. And I wanted to point out that the key to a successful mine is to let nature do as much of your work for you as you possibly can. And that goes back to what's been said about what information do we need, and what you were asking about a few minutes ago can be answered by saying, well, yeah, we can make various things from different feedstocks, but some are easier than others. And if you have only one type of feedstock, you can do it, but it'll cost you more. And it's not necessarily dollars, but it's trouble and difficulties and more mass to be launched and things like that. So it's always a trade-off, and it's not just a one sort of thing. I mean, there's in some of these documents it says the cutoff grade is 5%. That's obviously notional. We don't really know because we haven't done the trade-offs. Like any trade-off, there's lots of parameters. So, and you pointed out a lot of the processing parameters for some of the clays. So these are all things that need to be discussed among us. And a lot of the trouble I think we have is we talk past each other with our different jargon. And so I think we're all going to have to make more of an effort to understand what we're talking about. And I'm hoping as part of the ISRU community that we can help with that. And there are some conferences and even some short courses that may help. And I hope we can kind of disseminate those among everybody and see what we can work out, just understand each other a little bit better.
One last quick comment.
Yep.
So,
with the mic.
So, I've worked in the Apollo program, and what you say is exactly right. There's a huge overhead on learning each other's language, okay? So, we're in this for the long term, fortunately, and we really need to listen to each other, ask the right questions, talk to each other, and really establish a science and engineering synergism here, because we don't think the same way, which is great, okay? But we need to communicate and learn each other's language so we can really optimize the product. So.
Okay, thank you. So just before I let you run free, two things. The first is the polling sheets. Hopefully you've been filling them out. Please hand them in and then pick up the sheet for tomorrow. They really will provide useful feedback. And secondly, apologies to Jim Head. I realise I absolutely butchered the title of his talk earlier. So this time, with the power of punctuation...
I wasn't here. You're lucky.
Oh, okay. Well, the colon threw me. So his talk is called The Climate History of Mars. Pause. Was the early Mars climate warm and wet or cold and icy? And that's tomorrow in the Hess room at 1.
Now I'm anxious to hear what you really say. I could probably talk about that too.
Okay, so start again tomorrow at 8.